Now we proceed to present the actual algorithm implementing total order broadcast on top of consensus. And this is algorithm 6.1 in your textbook. So what you see here on this slide, on the left hand side is a specification of the components being used by the algorithm and the state being used by the algorithm and its initialization. And on the right hand side you see a diagram showing the actual layer structure of the implementation. So the algorithm we'll be discussing is this one here. So it's a consensus-based total order broadcast, and it supports these two events, broadcast and deliver. And inside is going to use as components, as underlying components, reliable broadcast. So it's one instance here, as well as consensus. Okay. So as you can see here, we are actually going to use not just one but many instances of consensus. So that should actually look like this. Okay. So there are many instances of consensus being used, and when we discuss the algorithm, it will become clear why that is needed. So for now, just notice that inside consensus implementation, a specific implementation of consensus component that is being used here can rely, say, on these abstractions of failure detectors or eventual leader detector, as we discussed. But for our purposes, implementing the total order broadcast, we actually don't care. So this specific detail is completely transparent to us. So as long as we have this consensus component as a black box, we actually don't care how it is implemented inside. Okay, so as long as we have that, and this provides us with these two events, propose and decide, and these two events satisfy the specification of consensus, we are going to be fine. So as regards the state, so the state has four variables. Unordered and delivered are sets of messages. Unordered is the set of messages that have not yet been ordered, and delivered is the set of messages that have already been delivered. Okay, so the names are actually descriptive, so they correspond to what they actually are. So now a variable round here suggests that there is some notion of round being implemented in the algorithm. So these rounds, as we will see, correspond to invocations of a specific instance of consensus. Okay, as you will see, the algorithm proceeds in kind of first accumulating a bunch of messages and then using a single instance of consensus to propose the accumulated batches as values for consensus. And then it is going to wait, okay, until decision is available. And once decision is available, the algorithm, as a specific process, will continue to the next round, and then it will invoke a different instance of consensus. So this wait variable here is used to synchronize between the rounds, so to make sure that the process does not proceed to the next round before it finished, and finished in the sense of reaching a decision in the current round. Okay, so now let's see the actual pseudocode of the event handlers. So now let's have a look at the event handlers. So the first event handler here is activated whenever we get a request to broadcast a message from the upper layer. So for example, from an application implemented on top of the total order broadcast layer. So for instance, that could be the seat reservation system that we have discussed. And whenever that happens, the handling of this event is actually pretty simple. So what we do, we basically just pass this request on to the underlying reliable broadcast layer. Okay, so we just trigger an event request to broadcast M at the reliable broadcast layer. And recall that a reliable broadcast layer guarantees that if a message is delivered by a correct process or for uniform reliable broadcast by any process, then it is eventually delivered by all correct processes. Okay, so the next handler here, this one, happens whenever reliable broadcast delivers to us a new message M from sender P. Okay, so what we do here is that we check if M is already in the delivered set, and we need that in order to guarantee the node application property, so we don't deliver these messages more than once. So if M is not in delivered set, then we add it to this unordered set. Okay, so this is the actual addition here. And what we add is actually a pair, a process, the sender of M, and the M itself. And we need to remember the sender of M in order to be able to reconstruct it whenever we eventually deliver M. And this is because the interface requires us to also supply the identity of the sender. Now, the next two handlers are the most important ones. So this one and this one. So they actually the heart of the algorithm. Okay. So to see what happens here, so let us consider a timeline of a single process. Let's say process P. So we discussed that algorithm has this notion of rounds. So initially the round is 1 and weight is false. Okay, so if this is indeed the case, then this condition here becomes true once we have some messages in the unordered set. Okay, so process P was just sitting and waiting, and then at some point it got some messages from the reliable broadcast layer, and it inserted it in the unordered set in this handler here, and then there is something in the unordered set. Okay, so there is something to order now. Okay, so at this point this handler is going to be activated. Okay, so what happens in this handler is as follows. So here we actually start up a new instance of consensus. Okay, and this instance of consensus is going to be identified by the round number. Okay, so this round number is passed as a name of the consensus instance. Okay, so in the Elixir terms, you can imagine that what happens at this line here is actually that we call start for the consensus module. Okay, and once the consensus layer is activated, then we trigger a propose event on this consensus layer, and we give it unordered as the value. Okay, so now if you look at the timeline of process P, so let's say here it receives some messages from other processes from the reliable broadcast layer, say one message and another message, and then these two messages enter the unordered set, and at this point, say at this point, unordered set is non-empty, and so it decides to start a new consensus. So consensus started here, so this is a consensus for round 1, and then it uses this consensus instance to propose its unordered set. Okay, so once that happens, so notice that what this handler does, it actually switches the value of wait to true. Okay, and that means that this handler here won't be invoked until wait becomes false again. And when wait becomes false again, this is only after we reach the decision for the currently active consensus. Okay, so before the current instance of consensus is in progress, a new value is not going to be proposed. Okay, so basically here we have some batch of unordered messages, and this batch is proposed. So notice that the same actually happens at other processes as well. So they will also get, so if this process got some messages, then this process also will get some messages, because we use reliable broadcast, right? So, and this process also initially at round 1, and it when it got these messages, then at some point it may decide, okay, so now I go ahead and I also activate consensus for round 1, and I also make a propose here. Okay, and notice that this process can actually see more messages, for example, than this process here. Why? Because we are in an asynchronous system, and so there might be another process that also broadcast some messages, and this process, let's call this process Q, and Q already has this message delivered, and this process doesn't have this message delivered. So these sets here, these unordered sets here that are being proposed, are not necessarily the same. Okay, and this is why consensus is going to be helpful, because we're now going to decide on the same set of messages. So that could be proposal of either of them. It can be proposal of P, proposal of Q, or maybe proposal of other processes that are out there, right? But only one of those proposals is going to succeed and become the decided value. Okay, so when this happens, when we get a decision, then this handler here is activated, and what happens in this handler is that we get this set of messages on which decision was reached in this specific round of consensus, and notice that we will only process the messages from the round in which we currently execute. Okay, so that might be the case that there are already multiple rounds of consensus in progress, because processes execute at different speeds and they can progress to the next round. But any specific process, it won't go to the next round before it is done with the round it currently is in. Okay, so this is very important. So when we get a decision for our current round, so what we do, we go over all the messages in this decided set of messages, and we also sort this set. Okay, so we need to sort it in some deterministic order, so this order must be deterministic. Okay, so we sort these messages in a deterministic order, and then we go over this sorted set of messages, and for each message we encounter, we trigger TOB deliver along with the source of the message, and then we remove the specific messages from the unordered set and we add it to the delivered set. And then we continue executing in this for loop here until we exhaust all the messages that have been decided. So once that happened, then now we are free to proceed to the next round. And we also change the weight to the false, indicating that next round becomes possible. So this new instance of consensus can be activated and proposal can be made. Just as a quick footnote, there is a minor mistake in the pseudocode of this algorithm in the textbook. So this mistake is fixed in the pseudocode that you see on this slide. And the mistake is in this for loop here. Okay, so if you compare the for all loop in the slide and in the pseudocode in the textbook, you will see what the difference is. So again, this mistake is very minor, and basically the pseudocode there is overall correct, but to be more precise, it's better to have it fixed the way as you see it here. Okay, so to obtain a consensus-based uniform total order broadcast implementation, the only thing that needs to be done in the protocol that we just discussed in this consensus-based total order broadcast is to replace reliable broadcast component with uniform reliable broadcast and consensus with uniform consensus, and the resulting implementation will be otherwise exactly the same, and it will implement uniform total order broadcast. Okay, so now let's have a look at an example of the execution so we can understand better what's going on in this algorithm. So here we have a time-space diagram, and we have 4 processes in our system, P, Q, R, and S, and these circles on the timelines that you see here, so these black circles, they actually correspond to the events of reliable broadcast. Okay, so the algorithm uses reliable broadcast as a building block, so it will broadcast messages via reliable broadcast and deliver messages from reliable broadcast, and these black blobs here, they correspond to the respective broadcast and delivery event of reliable broadcast. Okay, so this is important to keep in mind. So these arrows here with the light background, they're being used to represent the total order broadcast requests submitted by the upper layer. Okay, so let's see what happens. So the processes start off and they execute, and then at some point some broadcast requests happen. So P is requested to broadcast to TO broadcast message M1, and S is requested to total order broadcast message M2. Okay, so then they proceed and just disseminate these messages using reliable broadcast, as we discussed, and then these messages arrive at different processes, possibly at different times. Okay, so when they arrive, then unordered sets at the processes become non-empty, and that enables activation of a new instance of consensus. Okay, so in this specific example, the first instance of consensus of round 1 gets activated somewhere here. Okay, so that's not necessarily happens at the same time at every process, but for simplicity we can just assume that. And at this point we can see that process P has its own message M1, and process Q has message M2 of S and message M1 of P. R has message M1 from P, and S has message M2 from itself. Okay, so those are messages that we have, and as you can see, these messages are different. So the unordered sets of the 4 processes are not the same at this point, and this is reflected here. So the first round of consensus, okay, you can see that the proposals made by different processes are actually different. Okay, so P will propose message M1 because this is the only message in its unordered set. It is not aware of any other messages because M2 is still in transit to P. So Q already knows of both messages that have been broadcast so far, M1 and M2, and R knows about M1 and S knows about M2. So here they will activate consensus and they will reach decision, and decision will be the value proposed by one of the processes, right? So any value, any proposal value is valid here, and in particular the value M1, which is the value proposed by both P and R, is the one that wins. It gets decided, and so that will trigger a total order deliver event on all 4 processes in the first round. Okay, so at this point all processes will remove M1 from their unordered set and they will be free to proceed to the next round. Okay, so so at this point the right question to ask is what actually happens with message M2 here that did not get selected. Okay, so this entire value M1 and M2, this unordered set, is not the one that got decided. Because of that, message M2 still remains in the unordered set of process Q. So here you might be wondering, so what prevents messages from being starved? So why M2 will ever be delivered? So maybe it just gets stuck in unordered, and then new broadcasts are requested, and the new messages get enter into the unordered set, and then maybe M2 remains there forever, and because other proposals of other processes win. So the reason that does not happen is that we use reliable broadcast as the underlying message dissemination layer. And reliable broadcast guarantees that all correct processes will eventually get this message. Okay, so provided say Q is correct, if this is non-uniform reliable broadcast, or if even Q is incorrect, Q is faulty, then we use uniform reliable broadcast, then M2 will be eventually available to everyone. So, and this is exactly what you see happens in round 2 here. So again, proposals are different. So P proposes M2, Q proposes M2 as well, R proposes M2, M3, and S proposes M2, S3. But what is important here is that M2 is already everywhere. Okay, so M2 gets included in all the proposals, and even if they are different, so whatever decision is made, M2 is going to be delivered, in this case, in round 2. Of course, that depending on when M2 eventually received by everyone, it might be delivered in one of the future rounds. Okay, but in this example, so what happens, the corresponding point in time for this one is this. Okay, so at this point we have M3 delivered to R and S, and M2 is already available to everyone. Okay, so this is when round 2 gets activated, the consensus instance, a brand new consensus instance gets activated for round 2, and it reaches decision for a value M2 in this case. Okay, so this is the value decided, and this is the value that gets delivered in round 2. And as it happened before with M2, M3 get postponed to the next round. So in the next round, everyone has 4 messages, all 4 messages. So so this happens here. So this round 2 happens here. This is round 1, and this is round 3. So in round 3 we get M3 everywhere, M4 everywhere, and then the decision in this case can only be M3, M4 by the properties of consensus, and for that reason both M3 and M4 can be delivered in this case. Okay, so another important thing is that we said that all messages that are decided in the same round are deterministically ordered. Okay, so this is important, so we don't violate the total order. So what is being decided upon are sets. Okay, so M3, M4 is a set, but when we deliver these sets, we actually need to sort them. So in this case, the sorting is M3, M4. Okay, so M3 precedes M4, and then according to this sorting, M3 is delivered before M4, and that happens everywhere. Okay, so this completes this example.